Welcome back to the afternoon session. Our first speaker is Alden. He'll be talking about incremental prediction of sentence final verbs, humans versus machine.
Good afternoon. First I'll start with a brief outline of what I'll be talking about, motivation, why this is difficult and why we care. And then I'll talk about human verb prediction, machine verb prediction, and do some comparisons between them. So our motivation for this was primarily a simultaneous machine translation. So in some previous work, we tried verb prediction for simultaneous translation or interpretation, where we try to predict the final verb in verb languages and then put it into a translation system before that verb has been observed. But we did this in a very naive way, and we'd like to improve on this. We'd also like, and we'd like to do it with humans so that we can compare the performance of our system against humans, so we know you have a benchmark for what we could reasonably expect. Because somehow we think humans do this, and if it's possible, we'd like to use that fact to inform our system. And the problem of human verb prediction is itself intrinsically interesting, and no one has ever systematically studied before now incremental human processing in their final languages for the final verb. So our contributions, as I mentioned, were the first study of this in an incremental setting. We used crowdsourcing to perform our human experiments on the first crowdflower, and we informed our feature engineering for machine verb prediction based on these crowdsourced results. And this can be applicable to machine translation as well as help our linguistic understanding in general. So what's the problem? So in simultaneous interpretation, for example, if you're going from Japanese to English, suppose you only see this partial sentence, watashi wa in Japanese, and jimi and o ageta. So here, if you were to translate each word as it comes in, or what we would call a monotonic translation, you would end up with some English words in Japanese word order, which is not what we want. What we want instead is to put the verb in earlier, so that when we translate, we have a more natural sounding modern English sentence. And to do this, we want to predict the final verb. So previously we tried this with German using language models. So just to show that German also has these verb final instructions, we show that here. The language model we used in previous work was based on just the n-gram probability. So it's an I-based, it's actually a Kneser-Ney model scaled by the probability of a verb in the context. So what this means is that we score the context, or rather we choose the verb that maximizes the probability of the context, and then multiply that times the likelihood of that verb in the overall corpus. So this is intuitive, but it doesn't work very well. So accuracy is low, around 6% for Japanese, it's less than 4% for German, if you get rid of the obvious cases like so for example, is often occurs after another verb, and that's kind of cheating if you count that. So why is this difficult? So the distribution of verbs looks like this in our corpora. So in the pink, you have the Reuters news corpus in Japanese. On the right, you have the Kyoto Free Translation Task corpus in Japanese. So the news corpus is extremely skewed because news articles often end in verbs like reported. Whereas in the Wikipedia corpus, like the Kyoto corpus, you have more. It's still very Zipfian, but it's not quite as much so as the Reuters corpus. So, as I mentioned, for human verb prediction, we want to face this kind of comparison so that we have something to strive for at least. So to perform this, we extract 200 Japanese sentences from the development set of the Kyoto Free Translation Task corpus, which is a machine translation corpus. And we use a parser to segment the sentences into what are called insetsu, which are chunks, essentially, that contain one content word and one a more functional word. And this is a very natural unit of segmentation for a Japanese speaker. And we use crowdsourced judgments to test the human's ability to predict the verbs in a multiple choice setting. As I mentioned, we use Crowdflower with an additional pool of 56 participants. We removed 20 to get a Japanese fluency screening that we tested with, that we verified with highly functional but non-native Japanese speakers. And we gathered 5 judgments per participant. So the users were presented with something that looks roughly like this. So at the top you have a randomly truncated Japanese sentence that is truncated out of Unsetsu boundary, which means that it's not going to be truncated in some unnatural place. It's truncated probably after a noun or a case marker or a verb or something like that. And we also performed a separate set of experiments where we showed the entire context, so everything except for the final word chunk. And so they were presented with 4 answer choices. These were selected. So one of them is the correct completion. The other 3 were selected based on the frequency of the occurrence in the corpus. So they occur with a similar frequency in the corpus to the correct answer. Okay, so they're shown, it's like a game to them. They're shown partial sentence, and then they have to choose the right answer. So this is just a gloss to give you a sense for most of the audience who doesn't speak Japanese, what this would look like. So what did we find? We found that perhaps intuitively that the more of the sentence that's available, the higher the accuracy. We also found that on the full context set, the set that shows everything but the final verb, that accuracy is negatively correlated with sentence length. The average accuracy in this case is 81.1%. And we also found an effect of what we call case density, which is the proportion of case markers to the number of revealed words, or Unsetsu in this case, which is interesting because we know that these case markers provide important information about the verb. And I want to emphasize that it's amazing that we can do this at all, or that humans can do this at all, even in a multiple choice setting, because of the paucity of information we have in these situations. So for the machine experiments, we opted for linear classification, specifically allogistic regression. It's transparent, it allows for linguistic feature engineering, and we can ask specific questions based on our human experiments, such as does case information help? So for our first experiment, we classified the 100 most frequent lemmatized verbs in the training data. So we lemmatized them because Japanese, in particular, is morphologically rich, and if we try to classify fully inflected forms of the verbs, we would have no data. So we lemmatized them, and we were trying to predict the essential meaning of the verb, just based on the frequency in the corpus. And we eliminate all the confounding cases like copulas that come after verbs. Those are cheating. And there are details about that in the paper. So we tokenize this fact with the morphological analyzer and a pause tagger for German. And we use unigrams, bigrams, case markers, and the last observed case marker. We use the last observed case marker because in these, it almost certainly will mark the final verb, and not some intervening subclause or something like that, which can be confounding to a machine. So we train on we use the tags to extract for final only sentences that we train on those. So this is what it looks like for Japanese. So at the bottom, you see the language model, which, as we said, did not perform very well. It does improve as it gains more context, but not by much. And we can see that the difference between, there's a significant difference between unigrams and bigrams. So one key point here is that a discriminative model model works much better than a naive in-gram model. But another interesting thing are these kind of spikes in accuracy at the end. So recall that we also use features for the last observed case marker specifically. So we specifically set aside a feature for that because we know that this marks the final verb, and we see that it helps a lot, almost completely matching the diagrams by the end. We also did this for German. And again, so we performed the comparable experiments. So the language model does not perform very well. It does improve a little bit toward the end. Unigrams, bigrams, and case marker plus n-grams are closer in this case. But interesting here is that you don't see the spike at the end, but also that just adding the articles. So to capture case in German, we added specific features for the articles, which have some case information. And we can see that just adding that almost matches the diagrams in accuracy. So you can probably just skip the diagram altogether. So we can say that case information is important for this task in these languages. And as I mentioned, in German, just adding the articles can almost match adding all the diagrams. Same is true of Japanese at the end. So for the second experiment, we wanted to perform classification on the same task, on the same data we gave to humans. So as I mentioned, Japanese is morphologically rich, so we can't do this naively. If we just limitize like we did before, then we end up with basically random accuracy. And some of the answer choices in the dev set don't occur in the training data at all. So our solution to this is to just use a binary reduction to encode the answer choices directly into the feature vector. So we perform morphological analysis on the verbs themselves, and then we extract n-grams based on these morphemes and put them directly into the feature vector. So this, one, gives us more training data, and two, allows us to use clues aside from the primary meaning of the verb. So on the right, you have the same example from before. On the left, you have the segmentation. And then you can see that from this, you get n-grams based on these segments. So here we show how this is going into the classifier. So you have unigram, bigram tokens, and then in yellow you have the verb tokens. So we have the correct answer with unigram, bigram plus the verb features mapped to positive one, and then we choose a random negative example, a random sentence, and that has a different verb as a negative example. But we enforce the constraint that this verb cannot have any overlapping morphemes with the correct answer. And then at test time, we select the verb, or we select the verb that has the highest probability of a positive one. So we find the relationship with case density again, but it's very noisy, so I'm loath to say that it's conclusive. And far from random, we've managed, so the top line here is average accuracy, the bottom line is just a trend, and the larger the circles here mean that there's more data at those points. So we managed to get almost a 50% accuracy on this data, which is much better than we had when we were trying just limmatizing. So again, it is possible to encode this kind of information into a classifier. And again, we find the effect of sentence link on both the classifier arguments. So to show just quickly an illustrative example, we can show the confidence of the classifier over the course of this example. And all these orange circles here are case markers. So you can see the confidence of the classifier changing as a result of these. And this is more clear when we show the change in confidence from the previous position to the next word. So we can see that the case markers wildly change at least comparatively change the confidence of the classifier. And if we sort these by absolute change from just the previous word, we can see that almost all of the top ones are case markers, And the other one is the word after, which gives some tense information. So we can conclude that more context improves accuracy. We can do with a linear classifier what we couldn't do with just a language model. And encoding complex verbs is possible and makes this task feasible, even if we don't see the actual verbs in the corpus. And the final case marker in particular is important in Japanese. Thank you.
Yeah, I wonder how this translates to treating spoken language, because in spoken language obviously you will have more context control, but also in Japanese, for example, there are methods of actually front-loading the semantic content and you can drop almost all the arguments in any case. Do you have any thoughts on this?
So what was your question exactly?
How does it work with spoken language? I guess for text simultaneous translation is not a very important problem, so I'm guessing you're interested in spoken language.
So how does verb prediction work in spoken language?
Right.
This is an open question. I don't think anyone really knows. So obviously there are going to be some prosody effects in spoken language and contextual effects. So here we're forming this in an isolated sentence. But if the topic of concern is news, then maybe I should change my probabilities or whatever. But I think it's pretty well accepted in psycholinguistics, recent psycholinguistics literature, that people are making these predictions.
It's kind of very similar question, but have you tried with broader context, like the sentence before or the two sentences before? Because it could also give huge hints about what is going to happen in practice.
We haven't tried that, but it's something that we'd like to try. I think incorporate more context.
Any more questions? Yeah.
Do you think that it's would be helpful to have syntactic structure? So, for example, if you know that you're still missing this verb, and you could use a syntactic structure which tells you the different arguments.
Possibly. So to do this, we would have to somehow postulate syntactic structures that we haven't seen yet, or encode that in some other way. So one of the confounding factors are the relative clauses and things like that that don't attach to the final word. But they also provide other kinds of